Good evening, and welcome to the current installment of the SLAC Public Lectures. The lecture this evening will be by Simon Barr, one of our staff members in chemical engineering. Before I introduce Simon, though, I'd like to make an announcement, which is that CIPAC, the Kavli Institute for Particle Astrophysics and Cosmology, which is one of the laboratories associated with SLAC, has introduced their own public lecture series, which is going to take place in the alternate months from this one. Those will also be recorded. Those of you who are watching on YouTube, you can find the CIPAC public lectures on a different line of the SLAC YouTube channel. So this will all be publicly available there. The next of those CIPAC public lectures is in mid-February, Tuesday, February the 13th. The speaker will be Wendy Friedman, a very well-known astronomer. Wendy Friedman is the lady who measured the Hubble constant using the Hubble Space Telescope. Actually, that's why it's called Hubble. She's going to talk about the state of the universe. So please look out for that. That lecture will be on campus. And in general, the CIPAC lectures will oscillate between campus and SLAC. But I think with that information, you can find the announcement. It'll be, again, on Tuesday evening, February the 13th. Okay, please. And we will broadcast their information. If you're on our email list, you'll get that. Okay, now let's talk about the lecture for this evening. The speaker is Simon Barr, who, as I said, is a distinguished staff member here at SLAC. Simon did his PhD in Liverpool and then took a route which is very different from most of our scientists on the staff here. He became an industrial chemist, first for Dow Chemical Company and later for Honeywell, doing chemistry not in a little flask or a beaker with a couple graduate students at your side, but in those large things that you see when, for example, you pass the Chevron refinery in the East Bay. In the process, he became one of the great experts in catalysis in this sort of industrial chemistry. But of course, he always wanted to find out how those things really work. And so that brought him to SLAC, where he's now doing scientific investigation of what goes on in those huge devices that are important for industry and for our society. And so with that introduction, I'd like to welcome Simon, who will talk about catalysis, the hidden path.
Thank you so much for that wonderful introduction, and thank you so much for coming out this evening. I'm really excited to share with you some of my path, as was alluded to here, and something that I've been working on since I arrived at SLAC. So we're going to learn about catalysis tonight, and before we get into that, I thought I'd start with a little bit of my own history just to introduce myself to you. So as you can see, nothing has changed from my time at Cornell when I was a postdoc there to at SLAC now. I'm still as young as ever and still in the lab doing stuff. And that's what I enjoy doing. I'm an experimentalist. I love to be in the lab doing things, watching things happen, trying to understand how things work. And I'm still doing that, and that's really exciting. And SSRL, the Stanford Synchrotron Radiation Lab at SLAC here, gives me the opportunity to do that. So where did I start off? I started off in Northeast England in Newcastle upon Tyne. So that is Newcastle Brown Ale, the Tyne Bridge, and of course the land of Geordies. From there, as was introduced by Michael, I spent time in Liverpool getting my undergraduate and graduate degrees. Liverpool, of course, famous for the Beatles, the twin cathedrals, and the wonderful docklands. Well, those of you that know me know that I'm quite passionate about a certain sport, and that is football, or as you probably call it, soccer. So if you look at my life differently, you could say, well, I started off following Newcastle United. Then I started following Liverpool Football Club. And now, of course, in the Bay Area here, we've got to go out and support our San Jose Earthquakes. And we'll come back to soccer a little later in the talk. But I did take this somewhat odd detour by spending 29 years working in industry for Dow and UOP. And that's where I developed this passion, this understanding, this drive for understanding this thing called catalysis and catalysis science. And more importantly, understanding or getting a sense of appreciation for how a facility like we have here at SLAC, the Stanford Synchrotron Radiation Lab, can provide answers to some of the critical questions that we have to understand how our catalysts work. And that's what we're going to be talking about this evening. So let's just take a step back and look at the definition of catalysis. Catalysis is the increase in the rate of a chemical reaction due to the participation of a catalyst which is not consumed in the catalyzed reaction. So the science is catalysis. The thing, the substance we're going to study is the catalyst. How does a catalyst work? The way I sort of think about it is going across a mountain pass, right? We're doing a reaction along here, and this is energy. This is how much energy it takes me to get to the top of that hill. It's going to take me a lot of energy to get to the top of this hill, but if I can find a shortcut that can get me through a few little hills like this, I'm going to come out at the end a lot better off than going up over the top. And that's what a catalyst does. It provides a different pathway to give me the products that I want with less energy. I like to put a quote in that I think sort of sets the scene for something about what I'm going to be talking about. And here's a wonderful quote that I think. I'm a chemist by training, and so this one appealed to me. Chemistry without catalysis would be a sword without a handle, a light without brilliance, a bell without sound. I just love the sound of that, and that was by Alvin Mittasch in 1948. And once again, further in the lecture, we'll come back to Alvin a little bit later. Okay, so I think if I was going to ask the audience here, give me an example of a catalyst, I'd be quite surprised if this was not the example you came out with. It's the catalytic converter in your automobile, provided you don't have an electric car. You have this three-way catalyst, this so-called three-way catalyst inside this catalytic converter that's inside the exhaust. If we look closely inside of that, what do we see? We see porous channels where the gas molecules can come in and react. If we look even closer, this is now atomic scale. These are atoms I'm looking at here, just pictorially described. I have a little particle on here that the gas molecules can come in and react on there. So I'm getting the noxious gases coming in from my exhaust. They're going through my catalyst, and I'm getting less harmful products out the other side. Let's take a step back and say, okay, I'm driving my automobile. I've got to put something in that automobile. I've got to put gasoline in that automobile. Where does the gasoline come from? The gasoline comes from a refinery. Well, in a refinery, these things highlighted in blue here are all processes in a refinery that involve a catalyst. Now, I certainly don't have time today to go through what all these things are. They have funny names: catalytic reforming, hydrotreating, hydrocracking, things like that. The takeaway is that in a refinery, we've got to take the crude oil and make things like gasoline, jet fuel, diesel, fuel oil from those through these processes that involve a catalyst. Just to give you a sense of the scale of what we're talking about here, in an oil refinery, 50% of the world's gasoline production is produced by this process called fluid catalytic cracking. And in that process, in a typical catalyst, typical refinery, 50,000 pounds of catalyst are circulated through that reactor each day. The global demand for fluid catalytic cracking catalysts is of the order of 600,000 tons per year. So we're talking large volume for some of these catalysts. It really is important in our lives. But of course, we've got to look forward, right? We can't sort of just be happy with what we have. We need new catalysts that allow the production of chemicals and fuels that do not rely on fossil feedstocks. We want biomass resources, not fossil resources, to get our target chemicals. And of course, that is a huge opportunity for catalysis science. And that is what is driving us forward in terms of trying to come out with new catalysts for new processes or better catalysts for existing processes. What does the catalyst look like? Well, here's an example. They come in all sorts of different shapes, sizes, and you can see all sorts of beautiful colors here as well, right? A typical catalyst would have what I'm saying is nano-sized metal clusters on an inert sponge-like support. And we'll get into a little bit of what I mean by that, just so you have a sense for what a typical catalyst would look like. But they're sort of little pieces of spaghetti called extradates, or maybe little spheres here, or these monolith catalysts here that would be inside the catalytic converter in your automobile. The best way I can think about describing the support, this porous support, the sponge-like support that is the center of the catalyst, is thinking about your lungs, right? In your lungs, I have my trachea coming in here, so a big highway coming in, then it branches off, and then it branches off, and it branches off, and it branches off. So I have this huge surface area inside my lung. That's exactly what goes on inside a catalyst here. I've got this huge surface area for the molecules to come in and react, and the products to then diffuse out. So let's look at that a little bit more closely. So what I'm saying here is this porous support allows the molecules to access the active sites. See, here's my little piece of spaghetti here. This is a dimension of 1 millimeter here. If I was able to blow this up by a factor of 1 million, then I would see the individual atoms, these little metal nanoparticles on my porous support. But let's still take a little walk through what goes... It's playing over here. Okay, we'll ignore that. Okay, they're just playing over here. Another example of catalysis. Maybe you don't see catalysis in this slide, but we'll get to that, okay? What am I plotting here? I'm plotting two things. I'm plotting the grain yield here of English winter wheat from 1945 to 1998. So that's the red line going up here. So the yield per hectare is going up over this time period. I'm also plotting on this axis here the amount of nitrogen fertilizer that's added to the field to allow that crop to grow. So you can see there is quite a correlation there between the yield of that crop and the application of nitrogen fertilizer. Where does the nitrogen fertilizer come from? It comes from a catalytic process called the Haber-Bosch process. This takes nitrogen, hydrogen, and combines it to form ammonia. The ammonia is then converted into the nitrogen-based fertilizer. This reaction occurs under high temperature and high pressure in the presence of a catalyst where the hydrogen and nitrogen are combined to produce ammonia. This is a mega scale, world scale process going on. About 500 million tons of artificial fertilizer are made per year. Thinking about it a little differently, the manufacture of ammonia takes up 2% of the world's energy supply, or 5% of the world's annual natural gas production to make the hydrogen and drive the heat to make the reaction occur. Okay? Why is this important? Here's another way of looking at that graph I was just showing of yield versus application of nitrogen fertilizer. Now I'm plotting something a little different. I'm plotting then the world population here in blue with the world ammonia production here in green. What we see is right at this point here where the Haber-Bosch process was invented, discovered, and we were able to make artificial fertilizers. This goes up here. We were able to feed 7 billion people on the small, delicate planet that we live on. So it's not surprising then that this ammonia synthesis, development of this ammonia synthesis catalyst was classified as the most important discovery of the 20th century. So let's take a step back and say, okay, I've got my catalyst, I've got my nitrogen coming in, I've got hydrogen coming in. How is ammonia made on that catalyst? What actually happens at the atomic scale, on the atomic level? So my nitrogen molecule comes in, and it hits my catalyst surface. So my catalyst is this solid, this little metal nanoparticle on this porous support. The nitrogen molecule comes in, it bounces around a while, it sticks to the surface, and then it'll dissociate, and I'll get 2 nitrogen atoms on the surface. The same thing happens with the hydrogen. The hydrogen comes in, bounces around a little bit, sticks on the surface, dissociates into 2 hydrogen atoms. Then the nitrogen atom will react with a hydrogen atom, another hydrogen atom, another hydrogen atom, and now I get NH3, which is ammonia, then the ammonia would be on the surface, and then it has to desorb off into the gas phase. So just think a little bit about some of the things that are important then as I'm designing or trying to design a catalyst to do a reaction like this. I'm taking a nitrogen molecule with a very strong bond between these two nitrogen atoms, and I'm making a catalyst nitrogen bond. Now, clearly, if I'm making a very strong catalyst nitrogen bond, it's not going to want to react with a hydrogen to make this NH or NH2 or NH3. And let's assume I make NH3, I make my ammonia on the surface, but I've got a very strong bond between the ammonia and the surface. It's not going to desorb off, it's not going to leave the surface and go off into the gas phase so I can detect it, right? So the way to think about catalysis is like Goldilocks and the Three Bears. I can't have that bond too strong. I can't have that bond too weak. I've got to have it just right. And that's the heart of catalysis science, is developing the materials that allow Goldilocks and the Three Bears to occur. How did Alvin Mittash, he was the discoverer of the first catalyst that did this ammonia synthesis reaction, how did he develop this reaction? Well, this is one way to do it. He had 30 reactors working. It took him 2 years, and he tested thousands upon thousands of different materials. And saying, just put them in the reactor and see, did it work? Put it in the reactor, did it work? Put it in the reactor, did it work? Well, that is one way to do it. But we'll see, we do things a little differently here at SSRL at SLAC. But moving beyond that, we've talked about many different catalytic processes that are important, that allow us to have the standard of living of which we're used to here now. But what about processes that we don't have a catalyst? So let's think about methane reacting with oxygen to form methanol. So we know, we've all heard about shale gas, right? So that's basically methane gas. If we could convert that with oxygen to make methanol, now we have a liquid fuel that we can use to have a whole new series of petrochemicals coming from our methane. What we don't want to do is react methane and oxygen to make carbon dioxide and water. And that brings up an important point in catalysis, in the study of catalysts. We want to make the product we're trying to make and not the product we're not trying to make. And we call that selectivity. We selectively want to make methanol and not carbon dioxide and water. And in fact, in many, many chemical processes, in the refinery and petrochemical plants, the main cost in that process is not this part, it's the separating out the myriad of products that are formed. If we could only make a single product, we could save huge amounts of energy, huge amounts of money by avoiding that separation. Separation is always the most expensive part in any petrochemical plant. Okay, so how do we go about doing this? We do this a little differently. We say we're going to synthesize our catalysts precisely. We're going to test our catalysts. We're going to provide some theoretical understanding behind it. But then where do I come in? We come in up here in characterization. What do I mean by characterization? It's measuring the physical and chemical properties of that catalyst that's been made in the lab. So we're going to intimately combine all four aspects here to drive the discovery of new catalysts. The premise then that we go into this with is defined here. That the properties of the material, this thing I've talked about, that can't bind things too strong, it can't bind things too weak, it's got to bind things just right. The properties are determined by its composition and the physical and electronic structure, often at the atomic scale. So if we can go in and measure that and control that, then we can come out with a catalyst that is much better. So we can use that knowledge then to design those properties into the catalyst. And just to give you one little example of some of the subtleties in catalysis science, and there are many, many subtleties in catalysis science, and we don't have the time this evening to go into a lot of them. I'm plotting here this says onset temperature by some parameter here. It says average number of broken bonds on a surface. What am I talking about here? What I have is little metal nanoparticles, and they're all the same size, but different shape. This is a measure of activity for a given oxidation reaction, And this is then saying that the temperature at which that catalyst would do the chemistry that I'm occurring is not only dependent upon the type of catalyst that I have, but the shape of my nanoparticle that I have there. So just a subtle, very subtle aspect, but something that you sort of have to keep in mind. So if we could determine the size and the shape and the chemical composition of those metal nanoparticles, then maybe we'd have some new understanding. Now I'm sort of taking a step back and saying, okay, we're doing catalyst characterization. What are we going to try and learn? What are some of the fundamental questions that we're after here? So what properties are responsible for the reactivity? Hopefully from what I've talked about so far, you've got a sense that there's a lot of things that go into that. So what properties are responsible for the selectivity? We've said selectivity is so critical to the performance of this catalyst. Well, how is that determined? What's the structure of this thing I'm calling the active site? And we'll get into that a little bit more in terms of what I mean by the active site. And what are the reaction intermediates? What does that mean? Well, go back to our ammonia synthesis case again, right? I know I have nitrogen and I have hydrogen, and they come down and they react on my catalyst. Well, how do they react? Well, I've said it's N plus H to give NH, and then I have NH2. So those are reaction intermediates. The NH and the NH2 are reaction intermediates. I don't measure those. They're stuck on my catalyst surface. I never measure them in the gas phase. They're present there on my catalyst surface. So then the characterization, if we can measure all of this, this would allow the rational design of new catalysts or improved catalysts for existing processes. So as Michael mentioned in the introduction, this is kind of what we're dealing with. This is a typical reactor in an oil refinery. So how do we study the catalyst inside of this? It's at high temperature, high pressure. You've got gas flow going through there. How do you do that? Well, we're at SLAC National Accelerator Lab. We have the Stanford Synchrotron radiation light source here. We use X-rays, just like Superman. We can see inside things using these X-rays. So the synchrotron, which is at SSRL, just up the road here, here's a beautiful shot that was taken at night here, has an intense source of X-rays to allow us to probe the structure of those catalysts, often at the atomic scale. So let's take a look inside SSRL, and what do we see? If you go inside of SSRL, the first thing you see is an awful lot of activity. There's often 30 different experiments all occurring at the same time, the hive of activity. This occurs because we have these things called beamlines. These sort of straight lines here, this is a length scale here, this is 20 meters, 20 yards. So these things are sort of 20, 40 yards long. This is my instrument that I'm using to look at my catalysts. In a way, I've sort of heard beamlines described as kind of like the off-ramp of a freeway. I've got to somehow transport the X-rays from the synchrotron to my experiment through a pipe that's kind of like the off-ramp on a freeway. Each of these beamlines, each of these things coming off here is optimized for a different technique, and we'll talk a little bit about that. So this length here going from the source of the X-rays to my experimental hutch, this is often 20 or 40 meters long, and more importantly, the synchrotron operates 24 hours a day, 7 days a week, and we have over something like 1,700 researchers coming in visiting us here each year. It's a very vibrant place, it's a wonderful place to work, and why do we want to do that? Well, there are two properties that we're going to take advantage of at the synchrotron for studying our catalysts. The first one is brightness, or the number of X-rays. I have very intense X-ray source, 1 billion times more than the X-ray machine if you went to the hospital because you'd broken your wrist, right? 1 billion times more. That allows me to look at very low concentrations of elements, because often in a catalyst, the amount of material that's active is a very small amount, and I want to go and measure that. The second property is the fact what I'm plotting here is this intensity versus energy here. This is photon energy, the X-ray energy coming out of the machine. And it's a continuous source. What does that mean? It means I can study all the elements in the periodic table. So no matter what my catalyst is made of, I can go and study it. No matter how much of that element is in my catalyst, I can come to the synchrotron and measure it. Another way to think of a synchrotron is like a Swiss Army knife. I like this analogy. I've got a Swiss Army knife in my pocket. I pull it out. I'm after something. I open it up, and I've got the tool that I want. I've got the screwdriver. I've got the corkscrew. Whatever it is I want, I've got the tool right there. That's exactly what a synchrotron is. We have these beamlines. Each of these beamlines are optimized for these different techniques that we use to study our catalysts. I mean, there's a lot of big words up here, and we don't need to get into what all these things are. The take-home message from this is the synchrotron gives us tools to study the overarching problems in the characterization of our catalysts. The technique we use is something called X-ray absorption spectroscopy. And the reason we want to use the synchrotron is sort of highlighted here. I can measure this in the lab, and it would take me days or weeks to get a spectrum that looks something like this. I come to SSRL, just up the road here, and I can measure this spectrum in less than a minute. And this gives me this atomic level structure of my catalyst, and so it gives me things that I cannot do in the lab. That's why we come to the synchrotron. That's why the 1,700 people come a year. That's why we operate 24 hours a day. How do we make this measurement? Really quite simple. We have our catalyst. We have our X-rays coming in from the beamline. Those X-rays can scatter off my catalyst. I'm not interested in those. They can diffract off the catalyst. I'm not interested in those. Or I can measure the amount of X-rays that are transmitted through my sample through this X-ray absorption spectroscopy, and that gives me the information that I'm after. But maybe I've mentioned this, that we want to study the catalysts under the reaction conditions. So inside this reactor is really how I want to measure my catalyst. Well, how do I do that? Well, I can measure the catalyst before I put it in the reactor. I can do my reaction. I can stop the reaction, and I can take my catalyst out. So I've got my before, and I've got my after. And one way to think about that is, let's assume you've got a Martian coming down to Earth, and the Martian only has access to your prenatal records and your death certificate. And he's trying to figure out, he or she's trying to figure out the complexity of human life from that. There's no way, right? So we want to go and study the catalyst while it's actually operating, while it's reacting. And we call that in situ catalyst characterization, to understand the complexity of what's happening in there. Let's get back to soccer again, something I really like talking about. Let's go back to soccer. We've talked enough about catalysts. Let's talk about soccer. Oh, no, we're talking about catalysts. That's right. OK. So let's think about reactants coming in, products coming out. Here's my black box. Here's my catalytic reactor. So this in situ thing, another way to think about it, is like studying soccer, knowing that the ball was in the field of play. Now the ball's in the back of the net. A goal's been scored, but how and who scored? Or if you're a baseball fan, the baseball's in the pitcher's mitt, and then it's in the fan's mitt in the stands. Or in football, the ball's at the line of scrimmage, and then all of a sudden it's in the end zone. That wouldn't be very interesting to do that, right? You want to watch what's happening. So let's watch what's happening in this soccer game. Ball's passed around, comes up to another guy, two people have heard it, hit it, comes across, hits his head, boom, overhead kick, into the goal. Isn't that more exciting than just looking? Or maybe I want to look at it from a different angle. Maybe I'll learn some information differently from that. Okay? So that's what I talk about when we talk about in situ catalyst characterization, or watching something happen in real time. So for my synchrotron here, I've got my beamline. I measure my incident X-rays. I've got my reaction cell here. I've got my gas coming over. I'm measuring what's happening, and I see the products that are coming out. So I'm directly probing the active catalyst. So an example of the sort of data that we obtain is shown here. This is data from a catalyst for making diesel fuel. And this is one of the prime things that happens in catalysis, that I make this catalyst in the lab, and I put it inside my reactor. But to activate that catalyst, to get that catalyst to do the chemistry that I wanted to do, I have to transform it somehow in the reactor itself. I can't do that in the lab. It's got to be inside the reactor. So that's what I do here. And to make this catalyst active, we actually have to heat it up while we flow hydrogen sulfide over it. Hydrogen sulfide's that smelly, bad egg smell, right? We have to pass hydrogen sulfide over the catalyst. We do our spectroscopy, and we watch what happens. So we're heating the catalyst up, ramping the temperature. Here, this is the temperature going up. Here's the time along here. And we continually record our spectra here. A lot of changes going on. That's telling me that the atomic level structure of my catalyst is changing as I change my process conditions. What's happening in this case, this is a fairly simple case, that I'm taking my catalyst that was like tungsten oxide, and I'm making a tungsten sulfide. So in other words, this is the ball in the field of play. This is the ball in the back of the net. This is now understanding the intricacy of how the ball got from the field of play into the back of the net. So how do we do this at the synchrotron? How do you do this at the beamline? Well, we're going to take this big reactor and we're going to bring it here to the synchrotron. Well, maybe we are, maybe we're not. Let's see. We have to get our gases, our feed in there, and of course, safety always comes first. We've got to design the process safely so we can actually do this and not hurt ourselves. We're dealing with toxic gases, flammable gases. We've got to be able to control the pressure. We've got to be able to control the temperature. So we design these wonderful systems here, bring these to the facility, and then we bring our reactor to the facility. Oh, wait a minute, that's a little large. Let's make it a little smaller. Oh, that's better. Okay, I know I can bring that to the reactor. I'll just shrink it down. I've got to get my X-rays in. I've got to get the X-rays out. I've got to be able to heat the catalyst to the reaction temperature. I've got to be able to operate it at the reaction pressure. And I've got to get the feed in and the product out and measure the activity of the catalyst. So we recreate the conditions of that big reactor in a very small reactor. And these are just some of the examples of things that we have used here at SSRL to do that. There's no single design. It all depends on the chemistry that I'm going to do. What temperature do I want to go to? What pressure do I want to go to? What element am I looking at? That determines the energy, the X-ray energy that I'm going to use. Whether it's a low energy, medium energy, or high energy. That'll depend on what's going on. How fast do I want to measure the catalysis that's going on? All sorts of things that go in. So we design these and validate these custom hardware for the experiments. And this is kind of what it looks like in real life. Here's all the stuff inside our experimental thing. There are humans actually doing the work, which is wonderful, and that's great. When it comes down to this is the key question that we want to ask ourselves, right? We've got this material. We want to know what ensemble of atoms, what's the structure of this thing that's going on that's responsible for the catalysis? Or, another way to think about it, going back to the sports analogy again, who scored the goal and how was the goal scored? Okay, let's get into a couple of examples then, just to illustrate some of the work that we have done here at SSRL since I got here a couple of years ago. First one, what I've called here the synthesis of higher alcohols from syngas. What does that mean? It means syngas is just carbon monoxide and hydrogen. I'm going to react carbon monoxide and hydrogen. Where am I going to get my carbon monoxide and hydrogen from? I get that from renewable resources, from biomass, or from shale gas. I can very easily make carbon monoxide and hydrogen for that. Then I'm going to convert that into alcohols. So now I have a liquid fuel again, or a source to go into the whole petrochemical complex. Understanding this is then the key to making this whole process viable. We don't know how to do that today. The work that was started off used much more expensive metals than we were interested in. Things like rhodium, molybdenum, ruthenium, strange-sounding metals, very expensive. We don't want to use those. We want to use what we call earth-abundant metals, metals that are cheap to use, so we can make the catalyst cheaply and make our higher alcohols. And the catalyst that we're going to study here is cobalt. That's our nanoparticle, supported on silica. That's our sponge, okay? The process that we're going to follow is to activate the catalyst. Maybe that's something you've gathered from what I've been talking about, is you've made this material in the lab. Now I'm going to put it in my reactor. I'm going to do something to it. In this particular case, I'm going to heat it to 450 degrees centigrade in a flow of hydrogen and watch what happens. Then to test my catalyst, I'm going to reduce the temperature to 250 degrees centigrade. I'm going to flow my hydrogen and carbon monoxide, that's my syngas over there, at much higher pressure, 20 atmospheres pressure. So in other words, I'm going to go from the ball in the field of play to the ball in the back of the net, and I'm going to try to understand what is going on there. So here's the warm-up. Here's the warm-up. Here's just trying to get things going, okay? The activation. Here's my spectroscopy that I measure at the beamline as I'm heating my catalyst up to 450 degrees centigrade at 5 degrees a minute in 100% hydrogen. Big spectral changes that occur. What does that tell me? It tells me this. I start off with something little cobalt oxide nanoparticles, and I end up with little cobalt metal nanoparticles. So it goes through from oxidized cobalt to partially reduced cobalt to metallic cobalt. But even more importantly than that, metallic cobalt exists in 2 different phases. I can tell which phase of cobalt that is, and I know exactly now the structure of this little cobalt nanoparticle. Okay, so that's the starting thing. Now I put my syngas over there, and I watch what happens again. So there's many spectra plotted here. This is now at 20 bar, 20 atmospheres pressure in flowing hydrogen and carbon monoxide at 250 degrees centigrade, and I see these changes in the spectrum. What does that tell me in this case? The following. What happens during the course of the reaction is the cobalt slowly changes to a cobalt carbide. I start to incorporate carbon atoms into the cobalt and make a cobalt carbide phase. And with time, the amount of that cobalt carbide phase increases. So I go from a structure that looks like this to a structure that looks like this. Okay, that's all nice and good. But is that relevant or not? Well, the answer is yes. This is what we call a structure-activity relationship. We're determining the structure. We relate that to the activity of the catalyst. So what I'm plotting here then is the selectivity to my liquid product here, to my alcohol, against the time of reaction, together with the amount of cobalt carbide that I get in my sample. So here's the amount of alcohol that I form. Here is the amount of cobalt carbide that's formed. So clearly there's a correlation between these two. Why is that important? It's important because now we know the gold scorer. The gold scorer is this. We want to form this cobalt carbide phase. So now we can go back to the lab knowing this fact, so we can then synthesize our catalyst to give us more of that phase, or give us more of that phase sooner, or a more active phase of the cobalt carbide. Next example is going back to this thing of understanding the molecules that are bound to the catalytic surface. Think back to the beginning of the talk where I was talking about the ammonia synthesis reaction. And I had my metal catalyst surface, and I've got the nitrogen coming down or the hydrogen coming down. I want to understand what's bound to the surface of that catalyst. So how can we do that? The example I'm going to show here is sort of illustrated here. My catalyst in this case is iridium on a zeolite support. What is that? The zeolite support, first of all, is my porous support. This is my sponge-like material. The only difference here then is that it's an ordered structure. It's a very ordered structure, meaning it's very crystalline. And the dimensions of these pores, these channels going through, of the dimensions of molecules. So this is a molecule fitting inside the pore of a zeolite. So that's the zeolite support. I have my iridium atoms bound to the surface of this. And we're going to do something very simple. Like often when you're starting to do something for the first time, you've got to demonstrate the feasibility that actually, the thought that you have is going to work. And that's what we did here. We said, look, we know how to make this where I have 2 ethylenes bound to the iridium. And if I pass carbon monoxide over there, I switch out the ethylene for carbon monoxide. So I go from this structure to this structure. So in other words, the intermediate that's bound to my iridium is ethylene in this case. The intermediate that's bound to my iridium in this case is carbon monoxide. Can I tell those 2 apart by my spectroscopy? And the answer is, yes, we can. This is wonderful the way this worked out. What I'm plotting here, 2 different spectra, and this is just a zoom in of this area here. As we go from the diethylene complex here in black to the dicarbonyl, the 2 carbon monoxides bound in red. We see there's a big difference here between these spectra. So the answer is yes. And why is that important? That's important because if we can identify the species that are bound to the catalyst surface, then we can use that information to go in and understand the reaction mechanism, which will allow us then to know what's important in our catalyst to go in then and design new catalysts. Okay, I think I better sort of wrap up here. What I'm hoping that you'll leave with this evening is a sense that what we're doing here at SSRL is driving new catalyst discoveries by determining the structure of that catalyst under reaction conditions. And it's also driving, it works both ways too. You know, the discoveries we make are driving new catalysts, but the need to understand and make new catalysts is driving the science of the catalyst characterization. It's driving us to do better stuff at the beamline, to develop the methodology that we need to do that. And of course, these new catalysts are desperately needed in order to provide sustainable processes for food, fuels, and the future. And before I finish, I've got to acknowledge some people here. This is my current group here, Adam Hoffman here, Alexei Bubnov here. They're here in the audience here, and they're looking forward to talking with you afterwards. And of course, a whole army of people that go behind what's going on here. And I'd like to thank you for your attention this evening, and welcome to any questions that you might have. Thank you.
So, Simon, thank you very much. We can take questions. So you each have a microphone in front of you. If you press down on the middle, something will turn red and you have the floor. Why don't you get recognized and then turn on your microphone, and then the whole thing can be recorded. So who would like to ask a question? Please.
I'll repeat the question so they can...
Okay, so my question is, when you're looking for a catalyst, do you have a bunch of gas, like theoretical gas, or there are so many elements, how do you kind of start from somewhere? Not like Elgin, like long time back. Even maybe did he have a gas? Kind of what
So the question is, how do you know where to start? Where do you start? You've got the whole periodic table there. How do you even start? How did Alvin Mittash decide where to start? And the answer is, of course, today, yes, we have some good ideas. We've got 100 years of research in catalysis science to go on. And so we have these building blocks. We have a sense of which elements do certain things, which elements are good for making chemical bonds, which elements are good for breaking chemical bonds, that sort of thing. We know that. With theory, we've developed some wonderful correlations now with these very advanced theoretical methods that are out there. So you have this, it's not like you just started from nowhere. You have this huge body of information. And so you have a sense that if I have this metal, so why cobalt for higher alcohol synthesis? Well, because there's all this published information out there that gave us an idea that, yeah, probably cobalt would do it. But catalysis science is very detailed. It comes down to intricate, which atoms are bound to which atoms, what's the shape, what's the size. And if it was that simple that we could just go out there and just mix something up, I'd be out of a job for a start. And, but yes, we're getting there. We have this information, and there's a lot more work to be done.
Please? Oh, excuse me. Does someone have their microphone on?
Please? Yeah, my microphone isn't working. Oh, maybe it is. Okay. I was wondering if you saw a parallel between homogeneous catalysis. For example, homogeneous catalysis with cobalt to make alcohols, whether the mechanism is similar or fundamentally different in the systems you're working with.
Yeah, so that's an excellent question in terms of, I've talked exclusively tonight about heterogeneous catalysis. I didn't make that point. But there are many different types of catalysis. Heterogeneous catalysis just means I've got a solid catalyst and my reactants are in a different phase, in the gas phase or in the liquid phase. In homogeneous catalysis, the catalyst is actually dissolved, just like dissolving salt, if you will, in a beaker of water. The catalyst is in the same phase as the reaction that's occurring. And I did not have time to go into homogeneous catalysis, but you're absolutely right. There are often similarities in terms of work that is being done in homogeneous catalysis that then translate over to heterogeneous catalysis in terms of reaction mechanism for sure. So yes, absolutely, we can learn from one and translate that to the other, or take a homogeneous catalysis and try and what's called heterogenize it. So you take that thing that's soluble. One of the difficulties with homogeneous catalysis, as I'm sure you're aware, is the catalyst is now in the same phase as my reactants. How do I separate then the reactants from the catalyst? At least in heterogeneous catalysis, the catalyst is a solid, and my reactants are either solid or either gases or liquids, and so separation becomes easier. But absolutely, yes, we can learn from that.
Here we go. My question is, do you see any fundamental difference in the mechanism of formation, for example, of alcohols from cobalt compared the homogeneous to heterogeneous? Is the mechanism the same, or is it fundamentally different?
I'm actually not totally sure about that. I'd have to go in and look at that in more detail. I'm not as familiar with the homogeneous chemistry, to be quite honest with you. I tend to focus very much on the heterogeneous, and that's a Weasley answer. I understand that. But I'd love to talk about that with you afterwards, for sure.
Let me keep you just a moment. There's some eager kids in
Not a problem.
Please.
You have this precious research tool here on there. How good are you at keeping it productive? Is most of the X-rays used, or are you fidgeting with setting up the next experiment most of the time?
Repeating the question is, how productive are you? You've got this machine that's working 24 hours a day, 7 days a week. How often are you using the X-rays? The reason I chuckle to myself is, I came from industry, and productivity is one of those things that we worry about an awful lot. Time is money sort of thing. At a synchrotron, yes, there's opportunity to be more productive. And that's one of the things that my group, as they're well aware, is trying to actually determine ways of doing that. In fact, we've got an experiment running right now where we're trying to measure two things at the same time. So while we're doing something to one catalyst, we're measuring the other to take advantage of the fact that we want to be more productive. We want to get that answer out. People think about that all the time. I mean, in some of the aspects that I didn't have time to go into today, they use robots to pick the samples up, put the sample in the beam, pre-align the catalyst, or pre-align the sample in the beam to make the measurements. So yes, productivity is something we do concern ourselves with. Sometimes it's out of our control because we're trying to do something so complex, so difficult. It takes so long to set that experiment up, but then you learn from that, so the next time you come, you have all that information, you know how to do the experiment better. Another example, this is more of a technicality now, but we've got Oliver Mueller, I think, in the audience here. And one of the things that he's working on, I've talked about doing this X-ray spectroscopy. And in that X-ray spectroscopy, we're scanning this photon energy as we're measuring the spectrum. Well, if I measure point and a point and a point and a point, it takes some time, maybe 15 minutes to measure my spectrum. If I could just measure that continuously, maybe I can measure my spectrum now in something like a minute. And that's the sort of methodology we're developing right now at SSRL to try to then, that directly goes back to efficiency. Sometimes we take 20 minutes to make our measurement because that's the only way we can do it. But we know we could get the information out in a minute or less if we had the capability. So yes, efficiency is one of those things we do focus on.
just make one comment about that? Can I have this? Yeah. Which is that in scientific research, the way you really make discoveries is when something happens in your data that you don't understand.
Absolutely.
So you can try and be as efficient as you want in collecting that data, laying it out, looking at it, but sometimes you just have to wait for the wetware to catch up. And our bosses are very impatient, but that's just the way it works.
Yeah, thank you for that comment. Absolutely.
Okay, please.
It is working. Good. My question is the following. Have your research helped, for instance, technology of turbines? When you move from small scale to larger scale, you have, of course, problem of mixing of gases and fluid dynamics, correct? So I don't follow catalysis technology for the past many years. So the question is, are there any advancement that you know of, especially in turbines, to reduce the NOxes and so on?
In specifically what I wasn't catching?
In turbines. So in turbines we used...
Turbines?
Yes.
Oh.
Turbine technology, we used, palladium or ruthenium as a catalyst sitting on zeolites or, honeycomb structures. When you go from small scale to large scale, the fluid dynamics, mixing of gases, all that has a huge effect.
Oh, absolutely.
So the question is, when you're doing your research on a smaller scale, does it actually translate when you move back to the industry where you have myriad of other problems, including catalyst dying on you?
I mean, maybe the best way that I can answer that is that the company, or the companies that I was working for 29 years, paid my salary to do this. If there was no value coming out of it, I would not have been allowed to do that. And so the answer is yes. Some of obviously, a lot of what I was working on I can't talk about, but generally, yes. I think it is acknowledged that the information that we gain from X-ray science translates to real reactors. And in fact, I mean, it's one of those things that we take great care, actually. There are many studies, and we talk about it all the time in terms of what is the gas flow inside a reactor, how uniform is the temperature inside a reactor, because we know small temperature changes can make a big difference. We know mixing is important, the preheating of the catalyst. So on all these little, as you're alluding to, there's a lot of subtleties involved in catalysis science. And so if we're going to make this measurement on this mini reactor and say it translates to something like this, we've got to have some understanding of that. And so this is where some chemical engineering needs to be done. Can we measure, and it comes down in the end to kinetics. Do the kinetics that we measure inside our little reactors, do they mimic then the kinetics that are measured in these larger reactors? And sometimes yes, sometimes no. Sometimes there is some disconnect there, and we have to try to understand what that disconnect is. But absolutely, the information that's coming out here is directly applicable to industry. There's no doubt about that.
So let's take these two questions and then we'll end. So, sir.
Concomitant with what the lady was just talking about, is there anything that you would deal with where you'd have in fluid dynamics, like in aeronautical science, the Reynolds number?
Oh, absolutely, yes. I mean, we calculate, for these little tubular reactors, we can calculate a Reynolds number from that, absolutely, for sure.
And I had a
That's
second
one of those
question.
things that we do concern ourselves with.
I've recently read that, I've read The Making of the Atomic Bomb by Richard Rhodes, which is a wonderful history of chemistry.
Absolutely, it's a great book.
And I found out recently, and I don't know whether it's nonsense or not, but now they say that there are easier ways to distill these radioactive materials and make fissile weapons. Would any of that be using catalytic science?
To make fissile materials using catalysis. I think certainly to purify the uranium to make uranium hexafluoride, Sure, I could see a catalyst maybe making that more efficient. I mean, I certainly know that the efficiency of making uranium hexafluoride depends critically upon the uranium ore that is used. And that is a whole science in itself. And yeah, I'm sure catalysis could be applied to something like that. That's definitely something that, well, I certainly hope we don't go down that path ever again. But yes, it's potential.
The reason I asked that was because the fear is that the smaller nations that don't have the ability to make huge plants could produce for themselves fissile properties and secretly build bombs. I didn't want to blindside you there with something that's out of the hydrocarbon industry, but I was just wondering if you had heard of that.
No, I personally have not, no. But it's certainly something as humans on this planet we should be concerned about, yes.
In any event, the hard part of that is the isotope separation.
Right.
And that's not a chemical, it's a physical process, and it's
Right.
just intrinsically extremely difficult.
Right.
Now you have to centrifuge it.
Okay.
Yeah.
So, sir.
What's that? How do we turn this off?
Okay, presumably the theorists somewhere are doing software simulations on the catalysts and so on. How does the results of that affect your research?
Oh, hugely. I mean, the theory is so critical to what we do. And that is, I think, one of the biggest breakthroughs that we've had, you know, is with the computational power that we have, the new codes that we have, trying to then do real calculations, if you will, to drive, you know, the discovery forward. I mean, it's certainly a guiding, and I'm part of something called SunCat, which is a combination of people here at SLAC and on Stanford campus. And the whole concept of SunCat is to use theory to drive the catalyst discovery process. And that nice little logo that I had that had the synthesis theory, testing, and characterization, that's the SunCat logo. I probably should have put that on there and acknowledge them. But that is the heart of what some of the new discoveries coming out are, because we can obviously calculate, we can calculate things that we cannot measure, right? Some things are just so difficult to measure, but we can make calculations that guide us down a certain way. But then we still have to go in and make those things and test them. And then that's the feedback loop, because maybe we don't get the answer that we were expecting. Well, why not? Well, because of this. Oh, well, then put that back into the theory. So you have this loop going around. And then the other aspect of that I'm going to add is what I say the theory of the spectroscopy. So we're making these beautiful spectroscopic measurements. We make all these measurements, and we get this data, and then it's like, okay, what does that mean? And so you need the theory to understand the spectroscopy that you've done as well. And that is coming along in leaps and bounds as well, and we use that on a daily basis to help interpret the measurements that we make. So theory is critical, absolutely, yeah.
Okay, so Simon, thank you very much.